Let's talk about the chain rule and how the units of it all works out. Suppose we're tracking or predicting a patient's temperature, and it was a little high. It's 39 degrees Celsius, but it's dropping toward the safe zone, so that's fine. I mean, 39 is kind of borderline safe anyway. So let's say we call g of t their temperature in degrees Celsius at time t measured in hours. And let's say this is our prediction, so dropping half a degree Celsius per hour, starting at 39 degrees Celsius. And I've written in the units very carefully here. Here's what it would look like as we track as time goes on. The temperature is dropping, and we've got degrees Celsius on the y-axis and hours on the x-axis. Suppose we want to translate to Fahrenheit, and we have a function conveniently named f for Fahrenheit, that you give it a temperature in degrees Celsius, and it gives you back the equivalent temperature in degrees Fahrenheit. And you might vaguely remember the conversion. That's how it goes. You can trust me today. And let's write out the units on that. It's 9 degrees Fahrenheit per 5 degrees Celsius, or 9/5 degree Fahrenheit per degree Celsius, times x degrees Celsius plus 32 degrees Fahrenheit. So the degrees Celsius would cancel, and you're left with degrees Fahrenheit. So what is the temperature in degrees Fahrenheit at time t? We've got g, we've got f. What do we do? Well, first we ask, what's the temperature in Celsius at time t? And then we have f convert that to Fahrenheit for us. So f of g of t, maybe not a surprise here in the chain rule chapter. And then what's the rate of change? Well, what do we want to know the rate of change of? What's the rate of change of g? That would be g prime. So take a sec to write out what is g prime. So that would be the derivative of negative 0.5 t plus 39. And that's just negative 0.5. And what are the units of g prime? Well, it's y units over x units, or vertical units over horizontal units. So that would be degrees Celsius per hour. What are the units of the rate of change of temperature in degrees Fahrenheit by time, as time goes on? Well, there's two ways we could do that. I mean, in general, we could just take this idea and say, what I want to compute is f of g of t prime, like that. So we could actually compute f of g of t. So version number 1, I could say f of g of t, well, f of something is 9/5 times whatever x was. X here is g of t, so that'd be g of t plus 32, and that would be 9/5. And what is g of t? Negative 0.5 t plus 39 plus 32. All right, and that is f of g of t. And then what's the derivative of all that? That would be the derivative of this, which is, well, you could imagine distributing this 9/5, and it would be 9/5 times negative 0.5 times t, and then everything else is just constant, so its derivative disappears. So we would just have 9/5 times 0.5, and that's our derivative. What would the units of that be? It would hopefully be degrees Fahrenheit per hour, because that's what we're asking about, rate of change in degrees Fahrenheit. So that's version number 1. I forgot a minus sign here, didn't I? There we go. Okay, version number 2 would say, let's skip that algebra and just use the chain rule. So how are we going to do that? That would be f of g of t prime would be, say it with me now, f prime times g of t, f prime at g of t times g prime of t. What is f prime? That's the derivative of 9/5 x plus 32. That would be just 9/5 And then what is g of t, g prime of t? We said it's negative 0.5. So we got the same thing both times. One thing to notice about this is that it's the product of the slopes. Right, one of the slopes was negative 0.5, the other was 9/5. And another way to think about this is, it turns out to be the product of the slopes. Let's take a sec to think about that. All right, and then what can we do here? What can we say about this? What was this 9/5? What was the units of that? It was degrees Fahrenheit per degree Celsius, right? And what was the units of negative 0.5 in our problem? That was degrees Celsius per hour. And ultimately we wanted this in degrees Fahrenheit per hour. So can you see how the degrees Celsius kind of cancels top and bottom and gives us the units we ended up wanting? So that's great. Now you might have noticed all these functions were suspiciously linear, like we just had slopes. You could say, well, if things weren't linear, just use the current slope at whatever g of t is. Another way to think of it is, we'll say, what if things aren't linear? Well, the main rule in calculus is if things don't look linear, zoom in until they do look linear. Just get a totally local view of this, and that's kind of what calculus is telling us with derivatives. So zoom in means look at f or f prime right in the neighborhood of g of t, whatever t currently is. All right. I forgot to say, I don't mean literally zoom in. I mean, calculus is all about kind of zooming in until things, at least this part of calculus is about kind of pretending that we zoom in. I'm not saying you have to literally zoom in on Desmos or your graphing calculator or something. Another important thing here at the end of the chapter is our alternate, hold on a sec, alternate chain rule notation. It's on page 107, 108 of our textbook. Textbook is currently version 4. And the upshot of it is sometimes when we want to say in the chain rule dy over dx, that's like the overall derivative, you can think of that as dy over du, where u is just some stuff, kind of the inside thing, times du over dx. And you can kind of get the feeling that the du's should kind of cancel. They don't really cancel, but the notation was kind of invented to help give us the idea that this is a good thing to do because they seem like they should cancel. You can kind of see that that's what was happening here, right? We had one derivative times another derivative, and the units at least do end up canceling. Now, we don't end up using this very much in chapter 2.5, but we do end up using it a lot in chapter 2.6 and in chapter 4. So we're kind of introducing it now. You should go read it in the textbook, but it's a much handier notation when we get to chapter 2.6 and some stuff in chapter 4. One other motivation for the chain rule that I forgot to mention, you might have heard of neural networks in machine learning and deep learning. And the way you train those networks is by finding out kind of what their current slope is and make them kind of go in a good direction. And the way you find their slope is by using the chain rule over and over and over again. Fortunately, that's been done before. It's all in code. It's all automated. We don't have to do it anymore by hand, but it is a very interesting application. It's called backpropagation in neural networks.